In this video, I will show how to extend the approach to systems with multiple output quantities. Before, we had only one functional relation. Now we have multiple functional relationships that are all dependent on the same input quantities. For convenience, they can be written as a vector equation. Of course, each equation could be treated individually, but there's another way and it will provide additional information. The first step is to extend the sensitivity coefficient by adding rows with the partial derivatives of the additional equations. This matrix is also known as the Jacobian matrix. The covariance matrix describes the uncertainties and is the same as before. The matrix is quadratic and its size depends on the number of input quantities. The diagonal elements are the variance and the off-diagonal elements contain information about the correlation between the input quantities. The same equation is used as in the case of one output quantity, but this time all factors are matrices and matrix multiplications will be performed. The result is the covariance matrix of the output quantities. The structure is the same as for the input quantities. The diagonal elements describe the variance of each output quantity and the off-diagonal elements the covariance between the quantities. Of course, the dimensions of the matrices are such that all operations can be performed. One application of this method is the transformation of coordinate systems. As an example, the transformation between polar and Cartesian coordinates in 2 dimensions, which I will illustrate now. A polar coordinate consists of a radius and an angle, visualized as a point in an arbitrary parameter space. The radius and angle shall have also an uncertainty, which can be described as an ellipse in the parameter space. This point marks a specific position in a 2D plane, which is why we should use a better representation of the polar coordinate system. The 2D plane can also be represented by a Cartesian coordinate system. Now we have already transformed the point's polar coordinates into Cartesian coordinates, but how do we deal with the uncertainties? As you can see, the ellipse representing the uncertainties has been deformed. I assumed a large uncertainty to illustrate the deformation better. In real-world cases, the uncertainties should be small so that the approximation remains accurate. The first step to transform the uncertainties is to build a local Cartesian coordinate system around a point, which approximates the original polar coordinate system. One thing to highlight is that the components of the Jacobian matrix describe the axis of the local coordinate system. The uncertainty ellipse can now be drawn in this local Cartesian coordinate system. The idea is similar to what you know from a map, which is a local approximation of the globe. The Jacobian matrix describes the relation between a local coordinate system and a global Cartesian system, and this equation performs the transformation. Now I want to highlight something interesting. We started with uncorrelated uncertainties in the polar coordinate system, but the transformed uncertainties are now correlated. The reason is that due to the point's position, the x and y components get mixed and are no longer independent.